So Thomson discovers the electron. He creates the plum pudding model of the atom, which is where you have the atom, which is made out of positive stuff, and the negative electrons are embedded in it like plums in a plum pudding. Okay, then after that, we get the nuclear model of the atom. Okay, so remember, Thomson's plum pudding model, there's no nucleus. It's just positive stuff with negative electrons embedded in the positive stuff, just stuck right in there. Okay, the atom's mass is all spread out throughout its whole size. Um, and yeah, so the nuclear model came from these three lines of evidence, or two lines of evidence in one model. Let's have a look at them. First of all, the Geiger-Marsden experiment. Geiger and Marsden were students of Rutherford's, and they had this experiment also known as the gold foil experiment. Gold foil. And it's called that because there was a sheet of gold foil involved, a source of alpha particles which shot at the gold foil. It's green for glowing and radioactive. Here's the glowing radioactive green stuff. Alpha particles can't penetrate very far, so let's put a hole in there. Good. And they would shoot the alpha particles towards the gold foil to see what happens, right? All the way around, they had some special photography film stuff that when the alpha particles struck it, they'd light up so we could see where they go. Now, most of the alpha particles just went straight through and hit straight onto the other side. Not that odd. Not that odd at all, right? The gold foil is really thin. This model, the atom, is kind of flimsy. Alpha particles might be able to just punch holes straight through these. However, some of the atoms were deflected. Sorry, some of the alpha particles were deflected. Some were deflected a little bit, so they would move off a little bit to the side. Some of them, however, were deflected a lot, pretty much bouncing straight back from the direction they came. They said that this was as if you were using a handgun to shoot a piece of tissue paper and the bullet bounced off the tissue paper and came straight back at you. They were very, very surprised. What Rutherford concluded in his atomic model was that there must be a very, very dense area of matter, dense enough to stop the alpha particle. Not only that, it must also be positive in order to repel the alpha particle back the way it came. Okay, so dense matter might be enough to deflect it like this, but it needs to be positive in order to push it back the way it came. So we now have Rutherford's atomic model, which is where you have a very, very tiny, dense, positive nucleus. It has all the positiveness in it, lots and lots of positive in there. And around the nucleus, he knew the electrons weren't in the nucleus because that would make it neutral. So the electrons he assumed must be around the nucleus, and he thought maybe they orbited kind of like planets orbiting the sun, right? There's an inward force, which in this case is the electrostatic attraction, and there's a sideways velocity keeping them in a circle, okay? So the electrons can orbit around the positive nucleus like this. That's the gold foil experiment and Rutherford's atomic model, what he thought from it. Now, the only addition we need to this is Chadwick's discovery of the neutron. Chadwick, it's very, very hard to discover the neutron, right? Protons, electrons, not so bad because, well, protons are hydrogen, right? If you take the electron off hydrogen gas, you get protons. They already had that down pat. Thomson discovered the electron, and he discovered it using magnetic and electric fields. Neutron, no such luck. Electric fields, magnetic fields don't affect neutrons or barely affect neutrons. We can't sense them because they're neutral. So it's really, really hard to discover. He also has a more in-depth setup. So he had a source of alpha particles similar to what we had before. We have our box, and inside the box is something radioactive. I think it was polonium of some kind, spraying out alpha particles. Those alpha particles then hit a block of beryllium. I'm making my beryllium here pink because I know the beryllium oxide in your microwave is pink. They hit the beryllium, and out of the beryllium, when they hit the beryllium, nothing seemed to happen. Nothing was there. However, when he put some paraffin wax over here. Whoa, that's not a straight line. Paraffin wax here. Where'd I go? So it disappeared for a second there. Paraffin wax. Then, magically almost, out of the paraffin wax came protons, which could be detected by a Geiger counter. Geiger counters are those machines that detect radiation, like the ones in the TV show Chernobyl, where they're holding them around and they go. Anyway, so alpha particles hit the beryllium, nothing in the middle, but then on the other side, protons would be emitted by the paraffin wax for some reason, which could be detected. You take away the alpha source, that also stops the protons. So somehow energy from the alpha particles was traveling between the beryllium and the paraffin with no detected particles here. Turns out there were actually neutrons traveling in between there. They just couldn't detect them. They couldn't tell they were there. Chadwick used conservation of energy, conservation of momentum, in order to work out roughly the energy of a neutron, the amount of energy it had while it was moving, because he knew how much energy was going in from the alpha, how much was coming out from the protons. So he could work out roughly how much energy and mass and momentum the neutron had. He figured out that the mass would be roughly the same as the mass of the hydrogen atom, which made the masses of the elements make a lot more sense than what they had previously. So that changes this model from the plum pudding to the planetary model to pretty much still the planetary model. We just have protons and neutrons in the nucleus, as well as these orbiting electrons. Okay, there are some issues with this. These orbiting electrons, if you grab an electron, right, which is connected to all the electric fields around it, and you wiggle it around, that should create electromagnetic radiation. Atoms don't do that randomly. They should actually, if Rutherford's calculations were correct for how fast the electrons needed to orbit, they would orbit so quickly that they'd be producing X-rays and they'd crash into the nucleus very, very quickly. So obviously they were wrong, but this is still much more correct than the plum pudding model. That's all for me. Oh, except happy birthday to Meme as well.